Hey, I'm an astrophysics major and I'm gonna explain special relativity in the simplest, most intuitive way possible. I'll try my best to explain this as I would to my high school self because that stuff was and still kind of is pretty hard to wrap my head around. This will be one of a 2-video series on Einstein's relativity, where my next video will cover general relativity, the sort of stuff you saw in Interstellar. Let's get into it. Since the 1700s, Newtonian physics ruled the science world. Newton's laws could explain everything from falling apples to the motion of the planets. But even Newton knew his theory had limitations. His laws, especially when dealing with very fast-moving objects, started to break down when objects started to approach the speed of light. Then, in 1905, Einstein published his theory of special relativity. So, what's special relativity and why is it called special? Einstein's theory of special relativity would compensate for the conceptual holes in Newton's laws. Special relativity is called special because it applies to one special case, when objects move at a constant velocity in straight lines, meaning there's no acceleration, or they're at rest. This is called an inertial reference frame. Why straight lines, you may ask? Because objects that move in a curved manner have something called centripetal acceleration, which is still acceleration. 10 years later, Einstein would develop general relativity, a theory that handles acceleration and gravity, which were much more complex situations. The problem with Newtonian physics. Let's start with a fundamental issue that Newton couldn't solve. Imagine you're riding on a train and your friend Bob is standing on the platform watching you pass by. From your perspective, you're sitting still and Bob is moving backward. But from Bob's perspective, he's standing still and you're moving forward. Both of you are correct within your own reference frame. But the question is, who is really moving? You might say, obviously the train is moving, right? I mean, I can see the landscape go by. But here's the thing. You can't actually prove that the train is moving and that the earth is still, rather than the earth is moving and the train is still. Let me give you a better analogy. Imagine 2 astronauts are floating in deep void space with no planets or stars in sight. They start 1 meter apart, and later you observe that they're 2 meters apart. So, which astronaut moved? From the first astronaut's perspective, they stayed still and the second one moved away, but from the second astronaut's perspective, they stayed still and the first one moved away. Without some fixed reference point like a nearby star or some marker in the backdrop, there's no way to determine who really moved. This metaphor shows the core problem. There is no absolute reference frame. Or in other words, there's no universal stationary point in the universe. Meaning, if the universe is like a coordinate system, there's no origin, so to speak, to be a baseline for all other measurements. Where is that baseline when it comes to the train situation? Say the ground is one astronaut and the train is another astronaut. Where in that situation can we put a marker that is unaffected by the motion of those 2 frame of references? Thus, we don't really know who's actually moving. And now we've established that particles can't solve this problem, but what about waves? Maybe they could give us that baseline we need. If you put a speaker on a train, for example, the velocity of the sound waves aren't gonna add on to the train's velocity like a particle would. So maybe sound waves could serve as a universal reference point, right? Wrong. And here's the problem. Sound waves travel through air, and when you're moving fast enough, you're literally pushing against that air. If you're on top of a train and playing music on a speaker, the motion of the train itself creates a compression of the medium. Think of it like you're going on a very bouncy mattress, and when you fall onto it, you're compressing the mattress itself. Kind of the same deal if you're going on an extremely fast train, you can feel all that wind blowing in your face, right? That is the compression of the medium. This compression of the air changes the effective speed of sound from the speaker. Basically, the motion we're trying to measure causes disturbances in the medium, which in turn disturb the motion of the waves, which makes the sound waves unreliable as a constant reference. In fact, all waves we knew about needed a medium to travel. Sound needed air, water needed water waves, and seismic waves needed solid earth. And when you move fast enough through these mediums, you disturb them. So the wave speeds are never constant. Thus, neither particle nor wave can prove absolute motion. But wait, there's one wave that's different: light. In the 1800s, scientists thought light waves must travel through some mysterious medium called the luminiferous ether, kind of like how sound travels through air. In 1887, scientists Albert Michelson and Edward Morley designed a clever experiment to detect this ether. They pointed one beam to travel in the direction of Earth's orbit through space, and one beam perpendicular to that motion. So if the ether existed and Earth was moving through it as it orbits around the sun, the beam going with Earth's motion should be slightly slower, just like sound moving in air. Conversely, the beam pointed perpendicular to the motion should be going faster than the other beam because it's not being dragged by the ether. But what they found shocked everybody. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. This suggested that either the ether didn't exist or something much weirder was going on. At around the same time, James Clerk Maxwell had been working equations describing electricity and magnetism. In his equations, he used two fundamental constants: the permittivity of free space, epsilon naught, and the permeability of free space, mu naught. When Maxwell combined these constants mathematically, he got a velocity c equals 1 over square root of epsilon naught times mu naught. As we know, epsilon naught and mu naught are constants, and 1 over the square root of a product of constants is just another constant. And this constant matched the exact measured speed of light. So one thing this did was reveal that light is actually an electromagnetic wave. But more importantly, this proved that the speed of light in a vacuum is a fundamental constant of the universe. This is where Einstein's genius comes in. He realized that if there's no way to detect absolute motion, as in there's no universal baseline as seen by a two astronauts situation, and light travels at the same speed c regardless of the motion of its source or the motion of its observer as seen by the Michelson-Morley experiment, then one thing must be true. The speed of light in a vacuum is the same for all observers, no matter how fast they're moving. Let me give you an example of just how meaningful and confusing this concept actually is. Say light is traveling at 100 units per second and you are in a spaceship going 90 units per second in the same direction as the light. From your everyday experience, you'd expect to see the light moving at only 10 units per second relative to you, right? Because 100 minus 90. But Einstein says, no, you still measure the light going at exactly 100 units per second. If the speed of light must stay constant as we've established, and speed is distance divided by time, then something else has to change: time and space. If the speed of light is always constant, then time and space must adjust to make this work. These adjustments were described by the Lorentz transformations, developed by Hendrik Lorentz in the early 1900s. Originally, Lorentz thought that these were mathematical corrections needed because of the luminiferous ether, but Einstein realized that they actually represented something much bigger: the actual behavior of time and space. Here's how it works. If you're traveling at a high speed, time passes more slowly for you relative to someone at rest. The formula is T equals gamma T naught, where gamma is 1 over the square root of 1 minus v squared over c squared. So let's give an example. If you're traveling at 80% the speed of light, gamma is going to be 1.67. This means that 1 year for you would be 1.67 years for someone watching you on Earth. So yes, this means if you were in a spaceship going at the speed of light, you'd age far more slowly than people on Earth. Time dilation has been proven with measuring an atomic clock on Earth and comparing it to an atomic clock on a fast-moving spaceship. Objects moving at a high speed appear shorter. The formula is L is equal to L naught divided by gamma. Using the same example, if your spaceship is 100 meters long when at rest, it would appear to be only 60 meters long to someone watching it zip by at 80% the speed of light. And these aren't just numbers, they're the real effects of how motion warps space-time itself. Before we wrap up, there's one last idea in special relativity that I want to touch on. It's called simultaneity. It basically states that events that happened at the same time for observer 1 may not necessarily have happened at the same time for observer 2, who's moving relative to observer 1. Let me give you an example. Imagine once again you're on that train and you're sitting exactly in the middle of it, and Bob is on the platform. At the exact time you and Bob are aligned, 2 lightning bolts strike the ends of the train. From Bob's perspective on the platform, he sees both flashes at exactly the same time. But you on the train, you see the front flash first and the back flash second. Here's why. As we've established, the speed of light is constant no matter the motion of the observer. Thus, for you, both flashes are coming to you at a speed of c. But because you're moving on the train, you are going towards the front flash and away from the back flash. Thus, you see the front flash first and the back flash a little later. So what about from Bob's perspective? You guys were perfectly aligned at the time of the strikes, so what do the flashes look like for him? As we said, he's on the platform, so he's stationary. He's not moving towards one flash or the other, and since both flashes occurred at equal distances away from him, the light reached him at the exact same time. Thus, you might see the lightning flash as 2 events happening separately, while Bob sees them as 2 events happening at the same time. It's a matter of the observer's motion. Both perspectives are equally valid, and there's no correct answer about which lightning actually struck first. It depends on your reference frame. So theoretically, in an extreme situation, it's possible that 2 seemingly simultaneous events for one observer could have happened years apart for another observer. Thus, special relativity shows us that space and time aren't separate things. They're woven together into space-time. And because light is constant, we can mathematically prove that this space-time is actually flexible. Motion warps it, leading to time dilation, length contraction, and simultaneity. The faster you go, the more dramatic these effects become. They're always there, even in everyday speeds. They're just way too small to notice. For example, if the train was moving at 150 kilometers per hour, it would contract by less than 100th of the length of a hydrogen atom, which is why I use the extremes of 80% the speed of light, because that's when the effect starts to be more noticeable. And this is just the beginning. In my next video, we'll explore general relativity, where Einstein extends these ideas to include gravity and acceleration, leading to even more mind-bending consequences like black holes and the warping of space-time itself. Stay tuned for that, and thanks for watching.